Hi everyone, today a video in the bonding and structure topic looking at electronegativity, polarity and forces between molecules. So the forces that hold atoms together are all about the attraction of opposite charges. We've seen on the previous videos of this series that we've looked at ionic bonding, covalent bonding, metallic bonding. These are all really to do with electrostatic forces that either hold ions of different charges together, they hold the metal cations and the electrons, the sea of delocalized electrons together, or it's the electrons attracting the nuclei in covalent bonds and the electrons acting as kind of the glue. Now in covalent bonds, the electrons that are shared by the atoms will often not be shared exactly equally 50-50. And this will happen if there's an atom that is better at attracting electrons to itself than the other. And we give this the name of electronegativity. Electronegativity is the power of an atom to attract the electron density in a covalent bond towards itself. So it's how strongly, if I've got two atoms connected together in a covalent bond, how strongly does that one atom pull the electrons towards itself? Imagine it like kind of a tug-of-war kind of scenario. So you can think of it as the electron pulling power. The power of that atom to pull the electron density in a covalent bond towards itself and away from the other atom. Now when we consider these electrons not just as actual particles but as charge clouds, the term electron density is used to describe how the negative charge is distributed in a molecule. And we use something called the Pauling scale as a measure of electronegativity. It runs simply from 0 to 4. The greater the number, so 4, the highest number there, the more electronegative. So the higher the number, the more electronegative. And electronegativity depends on three main things: the nuclear charge, the distance between the nucleus and the outer shell electrons, and the shielding of the nuclear charge by electrons in the inner core shells. Now the smaller an atom is, therefore we're thinking of less electron shells around it, the closer the nucleus is to that outer main level of electrons. And therefore, because the electrons are closer to the nucleus is positively charged, the electron's negatively charged, there's electrostatic attraction between those two, and we have greater attraction. So the smaller the atom, the closer the nucleus and the electrons are, and the greater the electronegativity, because it pulls those electrons closer in. The other factor is the larger the nuclear charge for a given shielding effect, the greater the electronegativity. Again, it goes back to this idea of electrostatic attraction. The two things to think about for electrostatic attraction are the size of the charge. The bigger that is, the greater the electrostatic attraction. And also the size. The smaller the distance between the two charges, the greater that attraction. So typically, atoms that are small and have large nuclear charges for a given shielding effect have the greatest electronegativity. You can imagine the idea of the nuclear charge and the distance being that first one to do with how small the atom is, and the nuclear charge and the shielding of that nuclear charge being essentially if the electrons are much further out, then they are the outer electrons, the ones that are going to be involved in the covalent bond, the valence electrons, they're much more shielded from that nuclear charge by the inner shells, if there's many inner shells before it. So electronegativity increases going up a group, and it increases going along a longer period. So the most electronegative elements, therefore, are at the top right of the periodic table of elements. As we go up a group, the atoms get smaller. There's also less shells of electrons, and so there's less shielding by these electrons in inner shells. And so that increases the electronegativity. As we go across a period, the number of inner levels remain the same. We have the same sort of electron shell, but we are increasing our nuclear charge for that same amount of shielding, and therefore the atoms are also getting smaller. So both of those factors there, again, help to increase the electronegativity. So our most electronegative elements on this Pauling scale are fluorine, oxygen, nitrogen, and chlorine, stuff to the top right of the periodic table. This then leads us on to something called polarity. So polarity is the unequal sharing of electrons between atoms that are bonded covalently. So this idea of electronegativity leads into polarity. We have this unequal sharing of electrons because we'll have different electronegativities, different pulling powers of the electrons. And polarity is a property of the bond. So first of all, let's consider a covalent bond between two atoms that are exactly the same. When both atoms are the same, for example if it's dihydrogen, difluorine, HgF2, the electrons must be shared completely equally, because we have the same atom on both sides of this bond. If it's the same atom, they will have exactly the same electronegativity number, and therefore one of these atoms isn't better at pulling the electrons than the other. It's an exactly equal electronegativity, and so the bond must be completely non-polar. We have completely equal sharing of those electrons. You can imagine the electron density being kind of perfectly in the middle of that bond. And this is what we call a 100% covalent bond. Now, if you think of the electrons as being a cloud of charge, then we can draw out these electron density maps that I've shown on the right. So you can see there's one here for dihydrogen, H2, one here for dichlorine, Cl2. And so if we think of our electrons as being this cloud of charge rather than the kind of actual discrete particles, then a cloud is kind of uniformly spread out between the two atoms. It kind of looks almost a little bit like a sort of dumbbell shape. But generally, if you think about just an isolated atom, we'd have a sort of spherical distribution of charge. Normally this spherical distribution of electron density. We put two of them together, they kind of overlap in that middle region. That's a covalent bond. But essentially, our electron density, the size of the kind of the ball that surrounds each atom, is the same on the left as it is on the right. If we then consider a covalent bond between two atoms of different electronegativities, then we start to see some differences. So if we have two atoms that have different electronegativities, well now the electrons in the bond are not going to be shared equally between the atoms. So for an example, let's take hydrogen fluoride, HF. The electronegativities of hydrogen and fluorine are 2.1 and 4.0 on that Pauling scale, respectively. So the electronegativity of the fluorine is much higher than the hydrogen, and that's what we expect because it's further to the top and further to the right. Now, the electrons in the covalent bond then are considerably much more attracted to the fluorine than they are to the hydrogen atom. Think about the electronegativity being that electron pulling power, how readily it can pull the electrons towards itself in a covalent bond. So because the fluorine is more electronegative, it pulls the electrons more towards itself. And so the electrons are now more attracted to the fluorine than the hydrogen atom. And so when we think of these electron cloud diagrams, these electron density diagrams, these electron clouds are much more distorted towards the fluorine. And so we can see at that diagram there on the right that the size of the electron cloud around the fluorine is much, much greater than it is around the hydrogen. It's kind of now like this kind of distorted dumbbell shape. And so therefore we can see that rather than being sort of equally shared like in the hydrogen or chlorine examples above, now we have this sort of this unequal sharing, this distorted shape. Now what this means is that the fluorine end is therefore relatively negative and the hydrogen end relatively positive. You can imagine it being like a seesaw. We've shifted much more of our electron density onto the fluorine side of things than on the hydrogen side. And so in terms of the kind of relative charges, the fluorine side of it is now more relatively negative, it has more electron density. The hydrogen is more relatively positive because it has less of the electron density. So the fluorine has become slightly more electron rich, a bit more electron density on it. The hydrogen has become a little bit more electron deficient. It's lost a little bit of electron density. And so we show this by adding partial charges. And we use the Greek symbol delta. Looks like a sort of funny S. And so we use these partial charge symbols, these deltas, for delta plus and delta negative to each end. Now what this represents is a small charge of less than 1 electron's worth. If it was actual full charges, for example, if we had a proton, an H plus ion, and we had a fluoride, F minus ion, well here we'd actually write a full positive and a full negative. Because this is a covalent bond, it's not ions, it's an actual covalent bond, we haven't actually physically transferred any electrons, we've just sort of shifted the electron density more to one side than the other, and so we have to write these partial charges. So covalent bonds like this, where we have this unequal sharing of electron density between the two partners, are said to be polar. The greater the difference in the electronegativity, the more polar the covalent bond is. Now, while we say that our HF bond here is covalent, it does actually have some ionic character. Remember that ionic bonding is where we have our actual electrostatic attraction between oppositely charged ions. And so if we were going to make this into an ionic bond, we'd have to have an H plus, a proton, a cation, and we'd have to have our S minus anion, a proper actual negatively charged F minus. And so our ionic component of this would be actual H plus and F minus. That would be if we had our actual full transfer of electron from our hydrogen atom to our fluorine atom to make a hydrogen ion and a fluorine ion. Now here we haven't had actual full electron transfer, but we have had this electron kind of sort of shifting towards the fluorine. So we've not quite gone all the way to making it an ionic bond, but there is now some ionic character. It's some way towards the separation of atoms into charged ions. So it's possible to have an ionic bond that has covalent character, we'll see this in a bit, as well as here where we have covalent bonds that have some ionic character. It's also possible to have a 100% covalent bond like we saw for dihydrogen or dichlorine, because it's the same atom, so we have this completely equal sharing of electrons. But an actual 100% ionic bond is never possible. Even in normal kind of really typical examples of ionic bonding, like sodium chloride that we always talk about, that really isn't actually 100% ionic. While it is mostly ionic, we mostly have our proper sodium ions and our chloride ions, that's transfer of electrons, there will always be, because these electrons aren't actually discrete particles but electron clouds, there will always be some slight overlapping of these electron clouds, which makes essentially a covalent bond. So even in something like sodium chloride, it is an ionic bond, but it has some covalent character. A 100% ionic bond is not possible. So having talked about electronegativity and polarity, this now brings us on to intermolecular forces, the forces that exist between molecules. Now there are three types of intermolecular forces: van der Waals, dipole-dipole, and hydrogen bonding. And those are in increasing order of strength. So hydrogen bonding are stronger intermolecular forces than dipole-dipole, and they're stronger intermolecular forces than van der Waals. Now van der Waals forces act between all atoms and molecules. So it exists between every atom and every molecule that you'll see. Everything has van der Waals forces. Dipole-dipole forces, well, these act on molecules that have permanent dipoles. And hydrogen bonding acts between molecules that contain one of these very electronegative atoms, fluorine, oxygen, or nitrogen, they're the three most electronegative atoms, and a hydrogen atom that is covalently bonded. So first of all, let's look at dipole-dipole forces. We'll go into each of these in detail. So we said that polarity was a property of a bond. We looked at the HF bond, for example. Because we have that difference in electronegativity, it was a polar bond. But molecules with polar bonds may have a dipole moment. This sums up the effect of polarity of all the bonds in a molecule. So in molecules that have more than one polar bond, the effects of each bond may cancel out. And so overall, while they have polar bonds, the overall molecule isn't a polar molecule. The overall molecule doesn't have a dipole moment, we say. The effects of the molecule, though, may also add up and reinforce each other. And the key thing is that it depends on the shape of the molecule. So let's look at a few examples over on the right. The first one here is CO2. Now, we technically have polar bonds in CO2. We have carbon and we have oxygen. Oxygen is more electronegative than carbon. It's further to the right on that periodic table, so it's greater in terms of its electronegativity. We have a value of 3.5 versus 2.5 for carbon. And so therefore we have this polar bond, and we can write on our charges here where our carbon is delta positive and our oxygens are delta negative. Now, we can therefore draw a dipole. Now, dipoles are always drawn from the positive to the negative. Think about following where the electrons would go. And so those blue arrows at the top indicate the direction of the dipole. And we have a dipole going from the carbon to each of the oxygens. So while this molecule contains polar bonds, overall there's actually no dipole in CO2, and the molecule isn't a polar molecule. The reason for this is because of the shape of CO2. CO2 is a completely linear molecule. And what that means is that the dipole that moves to the right is exactly equal, but opposite in the sign of it, essentially opposite in the direction, to the dipole that's going in the left direction. So while we have these two dipoles, they actually cancel each other out. It's the equivalent of having plus 1 and minus 1. Putting them together cancels both out and you're ended up with 0. So this is why it depends on the shape of the molecule. We could have a polar bond, but we have to look at the shape to see whether those dipoles actually either reinforce each other, and therefore we have a permanent dipole and a polar molecule, or whether the dipoles cancel each other out. If we move down to the second example, we have CO2 again there, but on the right we have a water molecule, H2O. Now the shape of water is that it's a bent or a V-shaped molecule. And so we have again polar bonds. We have an oxygen-hydrogen bond on both sides. And so here we have our dipole here drawn from the hydrogen going to the oxygen. So the electronegativity of the oxygen is much greater than the hydrogen. It's much further to the right. And so therefore we have delta negative on our oxygen, delta positive on our hydrogen. So we can draw our dipole there shown in the orange arrows going from the delta positive hydrogens to the delta negative oxygens. And now the key thing is to think of the shape. The shape of the molecule is actually this bent V-shaped molecule. And so these dipoles actually end up reinforcing each other. They're not exactly going in opposite directions like they were for the CO2. They're actually both kind of pointing almost kind of towards each other in the same direction, and really both of them sort of diagonally going upwards. And so overall what this means is that we have an overall dipole moment generally across the whole molecule. The bottom of the molecule is more electron deficient, the top of the molecule is more electron rich. And so we can draw this overall dipole moment, shown in the blue arrow, which goes from sort of essentially going straight up. We're showing that we're going from, again, the electron deficiency to the electron rich areas. And so again, we have polar bonds, but because in the water molecule they don't cancel out, they reinforce. Essentially, you can think of them as vectors. Because they don't cancel each other out, they add to each other. Therefore, we have an overall dipole moment. And then finally, these examples at the bottom. So the one on the left is carbon tetrachloride, CCl4. Again, we have 4 polar bonds. Chlorine, again, we said was one of our electronegative elements. So we have chlorine being more electronegative than carbon. So we have a delta negative chlorine, a delta positive carbon. We have these polar bonds. And you can see here the dipoles that have been drawn going from the carbon to the chlorines, from the delta positive to the delta negative. However, again, because of the shape, actually a tetrahedral molecule like this, again we have to think of the shape, CCl4 is a tetrahedral molecule, all of these dipoles again end up cancelling each other out. And you can kind of imagine it as you have the Cl going up and the one sort of coming out with the wedge bond kind of cancelling out above and below, and then the 2 chlorines going to the left and the right, essentially cancelling each other out that way as well. And so overall, these dipoles end up cancelling each other out, and so therefore the CCl4 doesn't have an overall dipole moment and it isn't a polar molecule. We say it's a non-polar molecule. On the other hand, if we take chloroform, CCl3 with an H on, so CHCl3, this is now 3 chlorines and 1 hydrogen. Here, this is actually a polar molecule. Now again, we draw our dipoles going from the positive to the negative, so the carbon-chlorine ones are exactly the same. The chlorine is more electronegative than the carbon, and so we have these quite big dipoles here, from the delta positive carbon to the delta negative chlorine. We have 3 of those, but now we have our carbon-hydrogen bond, and actually carbon is what is more electronegative than hydrogen. It's further to the right. It's more electronegative than the hydrogen, and so now our hydrogen is delta positive and our carbon is delta negative in that bond. And so our dipole now goes from the hydrogen to the carbon. The key thing is that the difference between electronegativity between carbon and hydrogen is very, very small, whereas the difference between the carbon and the chlorines is much bigger. You can see that on the size of the vector, essentially the size of the dipole. And what this actually means is that there's generally an overall dipole going from the top of the molecule to the bottom of the molecule. All of those dipoles are pointing essentially down. And so we have an overall dipole that's shown over there on the right, that big downward arrow. And overall, it's a polar molecule because there's a permanent dipole. Now the next one to look at is van der Waals forces. So all atoms and molecules are made up of positive and negative charges. We have our electrons that are negatively charged, the nuclei that are positively charged. And so overall, our atoms and our molecules are neutral. They're made up from these positive and negative charges. And these charges produce very weak electrostatic attractions between all atoms and molecules. So if we imagine a helium atom, there's 2 protons, 2 electrons. Overall, this is neutral, but at any time, the electrons could be anywhere. We think of our electrons, of course, not as these discrete particles, really, but as this cloud of charge, these electron clouds. Now, this distribution of electron charge is changing at every instant. And any of these instantaneous charge distributions could mean that the atom has a dipole at that moment, but then in a different direction a moment later. So this electron cloud, the electron density essentially, is constantly sort of shifting around the molecule. And so our electron density is never essentially in the same place 2 moments apart. It's always moving around. And so it can be certain to be said that an atom will have a dipole at any point in time, and this will be a temporary dipole. So not a permanent dipole like we saw for molecules like HCl or HF, where we have that genuine difference in electronegativity and therefore an overall dipole, a permanent dipole, a polar bond. This is a temporary dipole, just because our electron density that is kind of always instantaneously moving could be more towards one side of the molecule than on the other. Now this temporary dipole can actually affect the electron distribution in other nearby molecules, so that they themselves are attracted to that helium atom for an instant. So we have a helium atom that has a temporary dipole, and then this induces a dipole in other atoms. And so we can see some of this in the diagrams over here on the right. At the top we have this uneven distribution of electrons in a helium atom, and next to that we have a completely non-polar helium atom. You can see again we have the delta negative and delta positive showing this kind of slight negative charge on one side, slight positive charge on the other. And then because we have this temporary dipole, that can then induce another dipole in the neighbouring helium atom. And so if we look at the one on the left, we have our delta negative on the left, delta positive on the right. This induces a dipole in the helium atom to the right of that, where we have delta negative on the left and delta positive on the right. So our positive and negative have linked up essentially. That's an attractive force. So van der Waals forces act between all atoms and all molecules at all times. And they are in addition to any other intermolecular forces. So that's the hydrogen bonding and the dipole-dipole forces. And these kind of instantaneous dipoles, these temporary dipoles, are caused by the change in position of the electron cloud. And so therefore, because it's based really on the electrons, the more electrons there are, the larger this instantaneous dipole will be, and the stronger the van der Waals forces. So the really key thing is that the size of the van der Waals intermolecular force increases with the number of electrons present. Atoms or molecules with higher weights, higher molecular weights, will produce stronger van der Waals forces because they have more electrons. So really what you look for is how big are the atoms and molecules that we're dealing with. The bigger they are, the more electrons they're likely to have, and therefore the stronger the van der Waals forces and the stronger the intermolecular force. And so this would explain why the boiling points of the noble gases increases down the group. The noble gases over in group 8 don't have any polarity to them. We can't hydrogen bonds, so van der Waals is the only force, intermolecular force that we have. And we know the boiling points increase as we go down, and that's because these are getting larger, they're getting increasing molecular weight, and therefore more electrons, greater van der Waals forces. And therefore, because the intermolecular forces are stronger, it takes more energy to separate them, to boil them essentially. It also explains why the boiling point of hydrocarbons increases with increasing chain length. Again, because with increasing chain length, more electrons, greater van der Waals forces, and therefore it takes more energy to boil them. Now the final type is hydrogen bonding. And hydrogen bonding is a special type of intermolecular force with some characteristics of a dipole-dipole attraction that we talked about a few slides ago, and also some characteristics of an actual covalent bond. And so while it's called a hydrogen bond, it actually isn't a covalent bond. It's just sort of bad naming essentially. So hydrogen bonding, it's called bonding, but actually hydrogen bonding is an intermolecular force. It acts between molecules. And so it consists of a hydrogen atom that is sandwiched, essentially, stuck between two very electronegative atoms. Now, for this to work, to have hydrogen bonding, there must be a very electronegative atom with lone pairs of electrons. We have our very electronegative atom, therefore it will be delta negative, and these will be attracted to the delta positive, the partially positively charged hydrogen in another molecule. Again, that electrostatic attraction. And there must be a hydrogen atom bonded to that very electronegative atom that will produce a very strong partial positive charge on the hydrogen, that delta plus. And so water molecules are an example of something that fulfill these conditions. And so you can see there at the top two pictures there at the top, we have our water molecules here. And the intermolecular bonding, the intermolecular force that acts between these, of course, remember it's not really a bond, it's actually just a force that acts between the molecules, it's much stronger than just the dipole-dipole forces that we've seen. And the reason for this is because our oxygen atoms have lone pairs of electrons. The hydrogen atoms are highly electron deficient, and so these exposed protons have a very, very strong electric field because of their small size. They have this partial positive charge, and because they're very, very small, they have a very strong electric field. And so the lone pair on the electronegative atom, for example on the oxygen in water, is very strongly attracted to the electron deficient hydrogen on another molecule. Now these are stronger than dipole-dipole forces, but they are weaker than covalent bonds. So again, remember that hydrogen bonding isn't actually a bond, it's an intermolecular force that acts between molecules. And only oxygen, fluorine and nitrogen are electronegative enough to form hydrogen bonds. And so therefore, if we look at some molecules and we have oxygen, fluorine or nitrogen with a hydrogen attached to them, we know that hydrogen bonding can occur. So the example at the top here is the water molecule. And when we're drawing out hydrogen bonding, it's always really, really good to draw out all the partial charges, so all the delta positives on the hydrogens, the delta negatives on whatever the electronegative atom is, in this case the oxygen. It's always very good as well, shown in the bottom example here, to draw out the lone pairs as well, because the lone pair essentially is what is being attracted to the hydrogen. And so we have a hydrogen bond donor and a hydrogen bond acceptor. And hydrogen bonds are always linear due to electron repulsion. So hydrogen bonding is always linear. You can see that you've got these kind of dashed lines going between the oxygen and the hydrogen. That's how we represent our hydrogen bond. And it's always completely linear because of electron repulsions. Another example would be alcohols. So at the bottom I've shown here ethanol. Ethanol can hydrogen bond to itself. So again, draw out the partial charges, so delta negative on the oxygen, delta positive on the hydrogen. We need to show our lone pairs as well on the oxygen. And we're going to use one of those lone pairs to draw a hydrogen bond. Here I've used this dashed line to indicate there's a hydrogen bond between the delta negative oxygen, the lone pair, to the delta positive hydrogen, that electrostatic attraction. And ethanol, alcohols, can also hydrogen bond to water as well. It doesn't have to be to itself, it can also be between different molecules. But again, we can have hydrogen bonding occurring because we have oxygen bond to a hydrogen in water, and we have an oxygen bonded to a hydrogen in ethanol as well. Now, the effect of hydrogen bonding can be seen when you look at the boiling point of common hydrides. Van der Waals forces are responsible for the general increase across a period. As we go across a period, or if we go down a group, we're going to get bigger molecular mass for our hydrides, and therefore we're going to have more electrons and therefore stronger Van der Waals forces. And so generally, if we think about going either across a period, for example from carbon to nitrogen to oxygen to fluorine, generally we get higher and higher. And likewise, once we go down our group, we also get higher and higher boiling points. For example, if I go down group 4, from carbon to silicon to germanium to tin, the boiling point of those hydrides, CH4 to silicon H4 to germanium H4 to tin H4, these increase because we're getting larger molecular masses, more electrons, and greater Van der Waals forces. However, what you can see is that the boiling point of the period 2 hydrides with oxygen, fluorine, and nitrogen are considerably higher than that of period 3 due to hydrogen bonding. And so if you can see here, what the sort of natural sort of shape we expect is what we'd see for the group 4 lines. We have CH4, then SiH4 being slightly higher, then germanium H4 being slightly higher, and then tin H4 being even higher than that. That's what we'd expect. But you can see that for when we have NH3, HF, or H2O, that these are much, much higher than the corresponding period 3, 4, or even 5. And the reason for this is hydrogen bonding. Remember, we said that hydrogen bonding can occur if we have oxygen, fluorine, or nitrogen bonded to hydrogens. And that's what we have in water, HF and NH3. So out of everything on that graph there, those are the 3 that can hydrogen bond. And hence, those 3 have much, much higher boiling points than when you go into, for example, period 3 or period 4. Now, hydrogen bonds are about 10% the strength of a covalent bond, but their cooperative effect can be significant. So while on their own, they're sort of a tenth of the strength of a covalent bond. If you have lots and lots of them all adding together, the actual sort of cooperative effect of that can be quite significant. We call it the Velcro effect. One tiny strand of Velcro really isn't going to do much, but if you have lots and lots of Velcro, then it can be really sticky. And so these hydrogen bonds, because they're not particularly strong, can be broken and remade quite easily, while the actual covalent bonds in the molecule are unaffected. And again, remember that hydrogen bonding isn't a bond. The covalent bonds are the actual bonds between the atoms. The hydrogen bonding is an intermolecular force. Now, in water's liquid state, the hydrogen bonds break and reform very easily because the molecules are moving around. But when water freezes and becomes ice, the water molecules are now no longer free to move about, and it's the hydrogen bonds that hold the molecules in fixed positions. And so you can see we have this kind of like, looks almost like a diamond-like structure, essentially these tetrahedral oxygen atoms here with our hydrogen atoms as well, and also lots of hydrogen bonding between them. And so we have this diamond-like 3D structure of ice, and in order to fit into this structure, the molecules are slightly less closely packed than in liquid water, and hence ice is less dense than water. So ice floats on the top of water. And this is in contrast to most other liquid systems. For most other liquids, it's the other way round. The solid is more dense than the liquid. So for most other liquids, if we condense it into our, if we freeze it into our solid, the solid would sink to the bottom, whereas with ice, the solid ice is on top of the liquid water. And this is absolutely crucial for life to exist. So, time to have a go at some questions. So if you'd like to have a go, pause the video and the answers will be on the next slide. So the first question was to define electronegativity. Electronegativity is the power of an atom to attract the electron density in a shared covalent bond. The power to attract that electron density towards itself. We then had to describe the intermolecular forces present in fluorine, CH3F and HF. So in fluorine, F2, this is a non-polar molecule. This is a 100% covalent bond. We have a bond here between two atoms that are the same. And therefore, because we have this 100% covalent bond, it's a non-polar molecule. We haven't got a hydrogen attached, so we can't do hydrogen bonding. It's not polar, there's no dipole, and so therefore the only intermolecular force that we can be dealing with here is van der Waals forces. The next one, CH3F. Now this is a polar molecule, it's tetrahedral. We have our very slight dipoles between the carbon and the hydrogens being delta positive, the carbon being delta negative, but that really is a very, very small difference in electronegativity. The much bigger difference in electronegativity comes from between the carbon and the fluorine. Fluorine being the most electronegative atom, so we have a very big, very strong dipole, a very polar bond here. Delta negative on the fluorine, delta positive on the carbon. And so this is a polar molecule overall. And so therefore, remember that we have van der Waals forces acting between every atom and molecule. So we have van der Waals forces, but now we have permanent dipole-dipole forces as well. And then finally, HF. Same as above here, we have a polar molecule between the hydrogen and the fluorine being much more electronegative than the hydrogen. So delta negative on the fluorine, delta positive on the hydrogen. We have our dipole, our polar bond. And so, same as the above, we have the van der Waals forces, we have permanent dipole-dipole forces, but because now we have one of the fluorine, oxygen or nitrogen bonded to a hydrogen, we can also have hydrogen bonding. Part C was to predict the trend in boiling points of the molecules above. And so we have to think about our trend in boiling points. What we're really thinking about is, well, what intermolecular forces are acting between them. We know that van der Waals forces increase with the size of the molecule, and so therefore that can be a factor to think about, as well as the actual strength of the intermolecular forces. And remember that hydrogen bonds are stronger than dipole-dipole forces, and those are stronger than just van der Waals forces. And so what we would expect here is for fluorine to have the lowest boiling point, CH3F to have in the middle, and then the HF to have a much, much higher boiling point than the CH3F. D was to predict the boiling point trend for HCl, HBr and HI. Now here, these are all polar molecules, so we're going to have dipole-dipole forces acting. We haven't got fluorine, oxygen, or nitrogen, so we can't have any hydrogen bonding. The other one is van der Waals forces. Now these all contain polar bonds. We have our dipole-dipole forces that are acting, but the key thing that's going to determine the order of this is the van der Waals forces. It's the size of the molecule. Remember, as the molecules get bigger molecular weights, we therefore have more electrons and therefore stronger van der Waals forces. And so we just have to think about our molecular weights. And so the trend would be HCl being less than HBr and HBr being less than HI. Part E would be to where would you expect HF to come in that series. If we were doing it just based off van der Waals forces, we'd expect HF to be before HCl because it has the smaller molecular mass. But remember that HF can hydrogen bond. We have fluorine, one of the fluorine, oxygen, or nitrogens, bonded to a hydrogen, and therefore we have hydrogen bonding, which is the strongest force, and so therefore the order would become HCl is less than HBr, is less than HI, and that's much, much less than HF. And then question 2, is methanol polar? Methanol is a polar molecule. Again, we have very, very small dipoles between the carbon and the hydrogen. Essentially, we can sort of ignore those. We have delta positive on the hydrogen, delta negative on the carbon, because of a very, very small electronegativity difference. The polarity of this molecule essentially is the really big factor in that is dominated by the carbon-oxygen bond. And so we have a very big difference in electronegativity here, oxygen being much more electronegative because it is further to the right. And therefore we have delta negative on our oxygen, delta positive on our carbon. And so therefore we have an overall dipole towards the right of that molecule, and so it is a polar molecule. We then have the boiling point of methanol being 65 degrees compared to minus 183 degrees for oxygen. And to explain the difference, given that they have exactly the same MR, because they have exactly the same molecular mass, we should expect that the van der Waals forces are the same. However, oxygen is a non-polar molecule. It's again 100% covalent bond. We don't have any difference in electronegativity, and therefore we don't have hydrogen bonding. We don't have dipole-dipole forces. The only thing that can act is van der Waals. Now, while the strength of the van der Waals forces will be exactly the same for methanol, methanol, we've just said, is a polar molecule. So not only will we have dipole-dipole forces acting, but we'll also have hydrogen bonding as well, because we have an oxygen bonded to a hydrogen. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on a tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.